Let's look at an example. How to find this two-port G parameter? These are the G equations, what we listed just now, and we want to determine the four coefficients. The first method is by the experimental measurements, according to its definition. When port 2 is short, we can get G11 and G21. When U2 is 0, G11 equals I1 over U1. Since port 2 is short, GC is short. So G11 equals GA plus GB. G21 equals I2 over U1. According to their reference directions, U1 is the voltage across GB and its reference direction is non-associated with that of I2, so G21 equals minus GB. Similarly, when port 1 is short, then GA is short. G12 equals I1 over U2 and also equals minus GB. G22 equals I2 over U2 and equals GB plus GC. We can find that this is a linear resistive two-port network, so it is a reciprocal two-port network. Its G21 should be equal to G12. The result proves this. Are there any other methods to determine the G parameters of the two-port network? Since the G parameters means to express a current by the voltages of the two ports, if we can write out their voltage-current relationships directly and pick out the coefficients, then we can get the equations of the G parameters. Let's try to write out the voltage-current relationships of these two ports directly. Using U1 and U2 to represent I1 and I2. I1 equals the current through GA plus the current through GB, which are GA times U1 and GB times U1 minus U2 respectively. I2 equals the current through GC, that is GC times U2, minus the current through GB. According to the reference directions, it should be GB times U1 minus U2. Rearrange the two equations. Pick out the coefficients of U1. I1 equals GA plus GB times U1 minus GB times U2. Similarly, I2 equals minus GB times U1 plus GB plus GC times U2. The result is totally the same as that of method 1. These coefficients are the G parameters. We can also find that G12 equals G21. For this network, if GA equals GC, this two-port is symmetrical. Now we discuss its G parameters. Besides G12 equals G21, G11 equals G22 as well, since GA equals GC. In other words, if a two-port has a symmetrical structure, then its electrical parameters should also be symmetric. It's called the symmetrical two-port. but a symmetrical two-port with the electrical symmetry may not have the symmetrical structure. Please pay attention to this. From the point of view of port characteristic, the two ports' external characteristics of a symmetrical two-port are totally the same. In other words, no matter which port is connected with the excitation, the responses of the two ports are the same respectively. Let's look at another example. Find the G parameters of this two-port. We can still use the experimental measurement to solve, and we will not show it here. Please think about how to find its G parameters by experimental measurement. Here we use the second method. Write out the port voltage current relationship directly. Okay, I1 equals the current through GA plus the current through GB. They are GA times U1 and GB times U1 minus U2, respectively. Then, applying KCL to this node, I2 equals the current through GB minus the current through voltage-controlled current source. They are minus GB times U1 minus U2 and G times U1, respectively. Put them in order. I1 equals GA plus GB times U1 minus GB times U2. I2 equals minus GB minus G times U1 plus GB times U2. You can find that due to the existence of the controlled source, G12 isn't equal to G21 any longer. Which means it's not a reciprocal two-port network any longer. This coincides with what we've learned in the previous video. We've summarized that a network with controlled source isn't a reciprocal two-port network any longer.